So I don't have my updated notes. All right, so let's see. I guess what we saw last time. So from the weakened homogeneity, we went through the expression for the molecular partition function. Again, we're only going to talk about homopolymers today, but we showed that we could write this as an exponential of some mean field term, and I think we actually had a factor of n up here. And then this is 1 minus big N squared over 2b squared, then sum over k. We had a divide function that depended on k, and wk, w minus k. All right, so remember these wk is the Fourier transform of this weak variations in the field. Actually, I think last time we denoted this as epsilon of k. I'm going back to w, just because that's what's in my notes. But the this w of k is the Fourier transform of w of r with w of r small. Right, and so there's an average value that we've plucked out that's w0 that we've put in this prefactor. We'll see that's just like a constant shift in the free energy. We're not going to care too much about it. And the wk is the Fourier transform of w of r. Assume that it's small, and for linear Gaussian chains, we get this result. And G is, this is, last time I think I did with this is G D of K. I'm just going to abbreviate it a little bit, it's just G sub K. This is the divide function. It's sort of like a form factor that tells us about the internal structure of a polymer. Yeah,
were we using W star instead of W naught last time? Are those ones the same?
Yeah, that might be.
Okay, that's fine.
Yeah. So W naught is W star from last time.
Yeah. Just a constant, right?
Yeah, it's a constant, and it's the integral of the field before we approximate it as being constant plus small things. All right, and so if you remember back to the Hamiltonians that we had, especially for this particular model, what we had was that H of W for this is the Edwards model. So remember, this is a polymer in an implicit solvent. So the only explicit molecule we have is the homopolymer. This was a field-dependent term that we don't necessarily need to worry about just yet. And then minus n log Q with Q up here. And with this substitution, we have, I'm sorry, in Q, now we have something that's an exponential of a constant, so we can plug that in. And the log of that, these guys multiplying each other, gives us a sum of two terms. The one that we care about is log of 1 minus this stuff. And log of 1 minus x when x is small is another thing that you can easily Taylor approximate. And so I'm just going to jump to kind of the final solution, and then we'll go through it in more careful detail, but I want to get it into the form that we have to discuss the subtleties of before we come back and do it a little bit more carefully. So if you use the fact that the log of 1 minus x is roughly minus x for x small, I mean, we've already argued that w is small, so w times another w should also be small. Then we can rewrite this thing into a form that will look like and again, this manipulation we will come back to and show in more detail. I'm not going to completely blow it off, but I just want to get to a point real quick. All right, so then we can say that H is going to be a form that looks like there will be a prefactor of 1 over 2v. And then when we do the 1 minus x thing on this, we can see that we're going to have a sum over k. So a sum over wave, sum over modes. Then there's a prefactor that also depends on wave number. And you can see why that would depend on wave number just from the presence of the divide function. So that's one of the things that's going to come out front. And then we'll have WK, W minus K. Okay. And again, like this, the manipulations that get us there and the specific form of what gamma K is, we will show for the Edwards model later, but what I want to talk about now is the fact that, so this thing is quadratic in W. And so when we write our partition function, right, which remember is the exponential of the free energy, this thing is going to be a bunch of the constants that we've ignored. This functional integral over the fields, and then e to the minus 1 over 2v, sum over k, gamma k, wk, w minus k. And whenever we do this weak inhomogeneity expansion that we truncate at order w squared, we can manipulate it into this kind of a form. Right, the gamma is obscuring a lot of the physics, right? Like all the polymer architecture stuff is buried in there, all of the interactions are buried in there, but we can get it into this kind of a form that we can actually solve. Right, and once we evaluate this integral, then we have an expression for the free energy, and that's something like you can analyze to look for like binodal and spinodal points and all that kind of stuff, right? To look for phase separation. So what I want to talk about, though, is the subtlety of actually evaluating an integral like this, because there's a lot of important small things that, well, Mike Valet and Glenn's group at the time was was figuring a lot of this stuff out while I was there in the office next door, which is kind of fun to talk to him about. So let me see. All right, so let's talk through some of these subtleties and point to the paper also. So this is stuff that's, I think, most clearly detailed in a paper by Mike Valet and Glenn Fredrickson. It's in Journal of Chemical Physics, 2014. And I'll refer to this paper a couple of times because there's a couple of really nice results in it that will come up today. But they talk through some of the details that you need to get right to evaluate this kind of an integral. And so this is what I want to spend today talking about. Okay, so there's a couple of points that we need to note. So the first one, this integral, right, this is a functional integral, right? And so it's we'll talk about how this thing is discretized in a moment, but basically what we're saying here is that we need to integrate over all the values of the function w of r, and specifically we're integrating over the real part of it. It's an integral over the real axis. So this is an integral over the real axis. And the analogy that I would make, and I think I've made this analogy a couple of times, is that when we do the Hubbard-Sturtanovich transformation to introduce this thing, we make it an analogy with Fourier transforms. Right, that was like the original analogy that we worked with to sort of justify this Gaussian integral. And if you think about the inverse Fourier transform, where you integrate over k, that's sort of what this integral over w is. Right, and when you do the inverse Fourier transform, that kernel that's in there is e to the I kx. And so that's a complex argument that you have, but k is only taking real values. Right, and so that it's the very similar thing that's going on here. All right. And that is despite the fact that W itself is complex values, right? And so the next point is that, and this is kind of a result from complex analysis that I've never taken a class in this, so it's a little fuzzy to me, but by adding or subtracting And an imaginary constant we can deform. Sorry, actually, I want to correct one thing. This should not be real axes, it should be real values. We can deform the integrals to be along the real axis. Right? And so basically what that just means is that we can add and subtract a constant to make W of R purely real, the thing that we're integrating over. Right? The thing that we're integrating over can be made such that it's purely real without any sort of consequences to how we're actually the final thing that we get. Then I'll make one more point here, then I'll make a new board. So if we're integrating over something that is purely real, right? So for W of R, that's purely real. This thing, right? So the Fourier transform of W of R, right? W of K and W of minus K are complex conjugates of each other. I haven't been with complex conjugates. Dagger, does that work?
Full dagger?
So I don't remember what that presentation is. We'll just say complex conjugates.
Yeah.
Really, the important thing can be summarized here, right? Our WK is going to be WK real part plus same wave number, but the imaginary part. And then W of minus K is going to be WK real part minus I, same imaginary part. And then for each of these, like the WKR and WKI are both just real scalars for a given K. And if you wish to convince yourself that this is really true, all you have to do is write down the Fourier transform of W of R for K to get the K mode and the minus K mode, and then use the Euler formula for e to the minus IKX. Make it like cosine X plus I sine X or whatever it is. And it falls out pretty naturally from all this. Okay. Any questions about these first 3 points? And really the meat of it is the thing that we're going to exploit the most is point 3.
So, it's not the most important thing, so we can put on this maybe, but like. What 2 is basically saying is that for each K, there is a constant. that you can project it on the real axes, right? Isn't that also reverting what that's saying?
So I believe 1 and 2 are mostly focusing on before we take the Fourier transform and go to K-space. Because point 3 sort of relies on W of R being purely real.
Okay.
And like 1 and 2 are kind of preconditions for being able to state part 3.
Yeah.
And you can sort of see, and like this is kind of getting to the point, one of the more subtle points that I'm going to make is that actually for each K, there's 2 constants.
Right.
Right? There's the real part and the imaginary part. And that's one of the kind of subtleties that creeps up into all of this.
Okay.
Okay, so the last kind of subtle point that I want to make has to do with really how you think about this pattern, right? Like, I mean, we think of, a 1D interval, like if you have some f of x, integral dx, that's the area under the curve. How do we think of a path angle? You guys have a way of thinking about these things?
A function, discretize it on points, and let each one of those values go from -infinity to infinity.
Yeah, so that's exactly how I think about it, right? So if we have some, let me see, I want to draw something that I can draw in real space and Fourier space. So if we do kind of a smoothed out box function, let's do that, because it's one I'm familiar with. All right, if this is our W of R, and this is not a great choice for W of R, like practically speaking, but it's fine. What this integral means is, as Josh just described, like you think about discretizing this on a computer, right, into a bunch of points. And then each one of those, what this integral is saying is that this represents the limit where this discretization is continuous, right, where you have these points everywhere. The way that we approximate this is as a product over all of those discretization points. And we'll see that there are m of those points. Integral dWr from -infinity to infinity. Right, so this is like, I mean, again, my understanding of quantum mechanics is maybe a little squishy, but this is my understanding of like the time slicing stuff that people do to deal with like path integrals in quantum mechanics. So we're doing a space slicing, and that corresponds to discretizing our function in space at points in space. And for each one of those points in space, so that's what we're producting over here, we're allowing the function to go from plus and minus infinity. So we're allowing this function to take on all possible values of points, for all possible values. And the argument that I want to make is that we can equivalently do this with the real version of the function in real space, or since the Fourier transform doesn't lose any information, you can also sum over all the allowed values of the function in Fourier space. Okay, so we can also say that this, so integrating all values of W, can be done in real space or in Fourier space. Space. The thing that we have to be a little bit careful about, and so actually let me say a couple of things. So this is kind of like a smoothed out box function. So the actual box function is the sine kx over kx. And smoothing it out just means like involving it with or multiplying it by a Gaussian. And so then if we had W of k for right? This approximation, when we take this W of, hey, so when we're doing the Fourier transform, we're always going to have a k equals 0 mode because that's the integral of the function, and we need to integrate over that. And so that's going to have W0 from minus infinity to infinity. Sorry, this is k equals 0. And then we have two real values that we need to integrate over for every plus and minus k. Right? There's WKR and WKI, and those two things show up at both plus k and minus k. So then we multiply by weight vectors, the WKR minus infinity to infinity, the WKI minus infinity to infinity. And so the last little wrinkle that I want to emphasize here, the whole point here is that I want to indicate we should have the same numbers of degrees of freedom in other words, the same number of integrals in R space and K space.
Why do we pick up the underbar for the K?
Because these are, well, my sketch here is just a 1D thing, but really these should be vector quantities, right? Because these are like X, Y, Z,
Oh.
potentially three-dimensional
okay,
positions,
okay,
right?
yeah.
So if we're doing three-dimensional, if we're taking the Fourier transform of a 3D function, and we have a 3D
Right, okay.
vector dependence. And k equals 0 doesn't have a separate real and imaginary part. Right, and so that's why I separate this one out just to make that explicit. Going forward for the rest of the little bit that we'll talk about today, I'm just going to denote this as like a product over k without the k equals 0 being separate, but just be aware that that one does need to be separated out and dealt with on its own. All right, so then we'll say this is the W infinity minus infinity to infinity. Okay. So these are the subtleties that I wanted to talk about or point out before we actually solve the integrals. And again, I full credit to Mike Foley for figuring this stuff out because it's a lot of like tedious subtlety to get right. All right, but with this in hand, we can come back to sort of the problem that we're interested in and solve things. And if you get these details right, then the rest of it turns out to be quite straightforward. Okay, so first let's talk about this stupid capital omega 0 that we've been sort of ignoring through all of these lectures. So we have this omega 0 from the Edwards model. Actually, let's just say from the Hubbard-Swiatovich transform. All right, so this is the normalization constant. I don't remember if we ever actually wrote it out, but it should be this one over 2 u naught integral dr. That's the form of it. Right, and then we can do the change of variables to write this in terms of its Fourier transform. This is one of those Fourier transform rules and tricks that we used last time a lot. You can say that this is path integral dw, u minus 1 over naught, b sum over Fourier modes, WK, W minus K. And since, well, we're assuming that we've done this deformation to put this thing so that W of R is purely real. So then we can say that this guy is going to be equal to, once we discretize this, discretize our domain, we'll have D, W, K, real, minus infinity, infinity, W, K, imaginary, minus infinity to infinity, e to the minus. So then we have sum over K, a number times its complex conjugate. Right, because remember W of K and W minus K are complex conjugates of each other. Minus 1 over 2 mu naught B sum over K B R squared plus W squared.
Does this not have the apostrophe product notation?
Oh, yeah, sure. Yeah. Thank you. I realize that I've skipped a lot of algebra here. Is there other questions, things you would like to see worked out? The cool thing about this is that now that we have it in this form, when we're doing these integrals, like K is just a label, right? Like it's just telling us which discretization point we're going to and letting the thing go from minus infinity to plus infinity. And they're all independent of each other. Right? Like what's going on at one K doesn't affect what's going on at another K. So you can do those integrals completely independently of each other. Right? And you can see that there's only one K dependence that's in here, right? So it's not, there's no magic going on with me saying that. And with the way that this is written, where it's an exponential of a sum of all the things that we're integrating over, this is all just a bunch of Gaussian integrals multiplied together. Right? So for each value of K, we can pluck out that value of K from this sum and associate it with the integral. It's e to the minus constant W squared. And that's the thing that we're integrating. Yeah, what?
So the right of the sum, that's each term, right?
Yes, they are both.
It's equal to like two something, yeah.
Yeah.
Okay, right. They're two, yeah.
All right, and so basically what we can say is that this whole thing is just equal to doing the same operation m total times W minus infinity to infinity e to the minus 1 over mu naught e. Right, we don't actually need the K label because all of those integrals are identical and independent of each other. And then this thing that's left here is just a Gaussian integral, right? We know how to do those, or we can look them up in Mathematica. Product over K to B 0 to the 1/2. And the thing that we've been insisting on with this prime is that the number of integrals that we have must be the same in real space and K space. So this is just 2i v 0 and then over 2, whatever our discretization is.
Something I think about.
Yeah.
Kind of maybe some point, we were very careful about the product having a prime,
Mhm.
that there was m terms in it.
Yes.
The summation in the exponent, that just always has m terms, just by the nature of, our choice to have I guess I'm thinking about a periodic box, and I guess what I'm trying to get at is, what I'm trying to understand is, why do we need to be careful with the functional integral, but not with the sum, terms of the summation?
Oh,
You see what I'm saying?
I mean, you should, and I guess I didn't make that explicit, but like, there needs to be the same number of terms in this sum as there are. Well, I guess there needs to be half as many terms in here as there are here. And really, because of the way that we set the problem up, where the integral over the fields that we're actually integrating here is 0, right? Because we define things so that integral dr w of r is 0 once we've subtracted out the mean field bit. The k equals 0 term is the integral over the fields. And so that is going to be like formally 0 in this anyway. We just have to make sure that the important thing is making sure that we have like the same number of modes that comes out of the end. What I vaguely remember Mike Belay telling me back in the day is that like there are a bunch of results, like if you're not careful about this, you end up with twice as many integrals than you might otherwise have, because you end up integrating over the minus km plus k things. And so you end up with like this raised to the m power rather than square root of m. And that screws up a cancellation that I think removes one of the divergences in the models. But I'm maybe fucking out of my ass a little bit on that. All right. Any other questions on this? Okay, so this was just an exercise to like solve the Gaussian integrals. Now we can finally go back to like the Edwards model. So again, the homopolymer, the implicit solvent, and the result that we got from last time, and actually get the expression for the free energy. So we had our partition function for that Edwards model. So this is again the Edwards model. It was z0 to the n over n factorial omega naught integral of the potential fields minus h, and here our h is so we have the same field term that we have over there from the normalization bit, and then minus n log q of I. And so the expression that we wrote down at the beginning of today, where we had q is 1 minus sum over modes, and then we said that the log of that can be written as just the negative of the thing, of the sum over mode part. If you plug in the weaken homogeneity expansion, so W-I-E, or weaken homogeneity expansion for Q, expand log Q, then what we get is H becomes approximately the first term I can write in Fourier space using the same thing that we did on the right over there, right? So it's 1/2V sum over K, W of K, W minus K. There's the N. And there's a mean field term that just gets added in. And then we will have plus little n big N squared over 2V squared sum over K, GK, WK, W minus K. Now, this sum and this sum are basically the same operation. So we can combine these two terms together. And so we can write this as, so we'll have 1/2v out front, sum over k, the big bracket here. 1/u0, and then plus this term, so plus little n big N squared over v gk, everything. Close that wk w minus k. These are sum. You have constant floating around from the mean field solution. And we're getting close to having something that looks like what we have over there. It's just a different prefactor, but I'm just going to call this guy our gamma k. So then we have h is 1/2v sum over k gamma k w minus k plus n. And now we're almost done with this. And so now we're sort of at the form that I was arguing for when we started today, where we can, anytime we're doing these weekend homogeneity expansions that we truncated quadratic order, we can manipulate it into this form, right? And that's basically what we've done here. And now we can throw it into here and set it up so that we can get it in the form like the integrals on the right. And so, see what's going to happen when we do that. So we'll discretize it over k. We'll again have, m modes. Then we have that constant that I'm just going to fold into the prefactor. And so I'll increment the prefactor by 1. So that's z1 to the n. N factorial omega naught. And then product over k. And it will be w r. And that will be k. The limits are the same. It's, overall the values of the function. Then we have e to the minus 1 to b sum over k k r squared. It's w k I squared. Oh, I forgot the times k. Actually, one thing here. So remember, this is the thing that came from the omega 0 that shows there. And one of the things when we did the sort of normalization part, the constants that were multiplying w are the real part, the imaginary part of the field, did not depend on k. Right. So that's why we just got the same thing raised to the m over 2 power was a pretty simple expression because the constants multiplying each of those integrals did not depend on the specific value of k. Here it does. It doesn't actually affect how we do the integration, but it does affect what we get for the result, right? We're not just going to get something that's k independent for the final result. Like the argument that I made about the integral over each k being independent of each other, that still holds, right? Because there's still only one value of k in here. So we can still take those integrals. It's just that the result that we get at the end is going to be k dependent. Right? Because we're not actually integrating out k. We're just going to each spot and allowing the function to take all the possible values. Right? But we're doing that at each individual k and keeping track of the result at each individual k. And so what we get when we do it this time is that becomes z1 to the n factorial constant product over k. Remember what we had over there when everything was just a constant, it was 2 pi b times u naught. And that's because everything was in the denominator multiplying. Here we have gamma k in the numerator, and so we end up with product over k, 2 pi v over gamma, which still has its k dependence. And this is still equal to the free energy, e to the minus beta. Again, for the purposes of evaluating these functional integrals, k is just a label for the particular variable. It doesn't actually enter into the integration itself. But then the result that you get from that integration still has that label associated with it for each one of those values of k. All right. Now that we're here, it's basically back to just simple, relatively simple algebra. Get to an equation for the free energy. But any questions in going from here to here, or through any of the stuff, the actual problem? And so if you wanted to do something for a different model, we can talk through that just for a moment. Where would things change? Well, if you change the polymer, if you were to change the polymer to like a different architecture, we haven't talked about it yet, but you could do like a star polymer, a star homopolymer or something. That's just going to change what shows up in the divide function, right? That's where all the like architecture stuff showed up. That was in this G sub k. What if you had a system that had a different interaction, right? Instead of this delta function contact repulsion through an implicit solvent, that's going to change to whatever you know. Right? If you had something a little bit more sophisticated for the interaction, or maybe you had Coulomb interactions of some kind, then this could potentially be k dependent, right? So that would change this part of it. But in the end, you can still manipulate it into this kind of a form. It's going to be a contribution from the potential and a contribution from the connectivity. And then as soon as you have it in a form where it's some k-dependent mess times w of k, w minus k, then you're basically done and you can just write down the answer. All right? And then, okay, so this is still kind of annoying and silly to look at, right? Because we have this product over k, it's not that intuitive. So let's do the final few steps of cleaning this up. Basically what that's going to amount to is taking the log of both sides so that we have an equation for the free energy rather than the partition function, which is not that easy to think about. So we take the log of both sides, so we get beta f, or free energy by kT, it's minus log z. I'm not going to deal with z1 or even explicitly with the omega maybe not, but just to kind of get all this stuff out, we'll have this log of material space time plus log of the knots. And then the key thing that we're going to have is that when we take the log of both sides, this log of a product over k is going to become a sum over k. And the square root is going to become a prefactor of a half, right? Because that's inside of a log. And so that's the big changes that we have. So it's become sum over k log of, let's go, gamma k over 2 pi b. And I used a minus sign somewhere to put gamma k in the numerator and 2 pi b in the denominator. And this k-dependent term, right, the one that has the sum over the modes in it, we're gonna talk about this one by itself for a bit, because this is the term that comes from the field fluctuations, right? The rest of this stuff is all mean field results, right? Like this, Z1 has the mean field solution buried in it. The ideal gas terms are up there. That's part of the mean field solution. This is the part that we're going to care about for now. Okay. So then our beta F, the fluctuations, the one that comes from these weak amplitude in that, it's weak field fluctuations. And say that this is 1/2 sum over k log 1 over u naught sorry, little n big N squared over b k. And inside the natural log, I'm going to multiply and divide. I'm going to pull out a factor of 1 over u0. Again, it's just going to be like a constant shift in the free energy. It's not going to matter. And I'm going to define rho mod as the monomer density. And we're going to multiply in here u naught over u naught. And so this whole thing is going to become 1/2 sum over k log u naught in gk. That's it, right? Oh. U naught, rho naught. We can just throw on the plus some F0 thing to represent that constant that comes from multiplying and dividing by using them. All right, and then the last step that we want to take is to restore the continuum limit and make this sum into an integral. Right, and so again, I'm going to play a game where I multiply and divide by b prefactor. So we'll say that this is beta fluctuation. This is going to have b over 2v sum over k. I'm being explicit about this k being a vector for the moment. We'll get rid of that. Not too long. Log of 1 plus u naught rho naught in gk. Again, I'm sort of ignoring the f shift, and then we restore the continuum limit, and so that's going to eat the factor of 1 over v. And the way that you do this in 3 dimensions, this becomes b over 2, 1 over 2 pi cubed, and then go dk log of plus u0, u0, and all right, so the conversion from v to over 2 pi cubed comes from switching between the discrete and continuum Fourier transforms. And then finally, so this is a 3D integral over k. We can, these functions, if you remember the form of the divide function, if you look back in your notes from last time, this only depends on the magnitude of k squared. It doesn't have an orientation part to it. So we can use that spherical symmetry. And this thing becomes v over 4 pi squared. So this integral over dk obeys like the same conversion to spherical integrals, spherical volume elements as like real space integrals do. And so there's a factor of 4 pi that comes out front. That's why the prefactor simplifies. And then for this flavor of the model, we will have integral over the magnitude of k now. K squared log of 1 plus u0 in ρ0 g k. So that's the next thing I wanted to talk about. This is
Lambda C.
yeah, so this lambda c, this is a cutoff on the upper limit of the integral. This is, you can say that it's an artificial cutoff. Is the problem that you run into with all of this is that this fluctuation term actually does not converge with the model that we've derived. Okay, and we'll talk a little bit about why that is, but this is basically the analytic origin of this phenomenon that's known in field theories, and I believe also shows up in quantum field theories, known as an ultraviolet divergence. Right, so there's basically a problem where as you go to higher and higher k, which is shorter and shorter length scales, the whole problem just blows up.
Oh, right.
And so this is kind of the analytic origin of this ultraviolet divergence.
So the main step from the previous line to this one is like basically spherical symmetry, right?
Yes, that's the one that I wanted to emphasize, yes. Yeah.
Just
And like, this is a simple enough thing, like we have the analytic equation for g of k from last time. And so you can just like plot this thing and try to integrate it and just see that it doesn't do anything sane. Like as k grows, it doesn't go to a bounding value.
sorry, can you repeat that?
It's like as k gets bigger and bigger, like the argument of this integral doesn't go back to 0.
Yeah.
Right, and so like the area under the curve is not finite.
Right.
Right. But with this in hand, though, like we can go back to our expression for the free energy. And basically what we have is all of the mean field terms, right? So the stuff that you can derive pretty easily using mean field approximation. And then now we have this fluctuation correction. And so we have the effect of field fluctuations on the thermodynamics of the system. So then we can do things like calculate the chemical potential and look for phase separation. You can calculate the osmotic pressure. And if you have phase separation, you should have states where equal pressures and chemical potentials. And so that lets you start constructing phase diagrams from these analytic models that are dirt cheap to evaluate. And you have fluctuation effects, right? And this is like, even if you did a full numerical SCFT, this term, its effects would not be there, even though we've approximated. But,
I have a dumb tangential question.
Yeah.
Is just in general when we're dealing with partition functions, free energies. Why do we typically use because we love to clump together constants that we don't care about, right?
Yep.
But then whenever we do free energies, why do we then break apart all of the log terms, if that makes sense, right? Like, couldn't you stuff the first line of that top line? That could all be stuffed together, right?
Yeah.
So
Well,
why do we just typically break those apart? Is that something that
so
that just so we can see each part kind of, is that kind of the Yeah, sorry.
Yeah, yeah, basically it's so you can kind of see each part, and I kept these together because their scaling with n is different, right? Like this one really is just a constant that's kind of irrelevant.
Okay, so
It
the
cancels
end
some of
scales
this.
we want to print.
But yeah, like you do Stirling's approximation on this,
Right.
then
Okay.
like getting the ideal gas terms, like you need to be a little careful about how you deal with these
Right,
things.
right, okay.
Yeah, that's really the only reason, unless I'm missing something, but.
Right, so it's the end scaling. Of
Yeah.
the size. That makes sense, okay. That's just something that I've always been wondering, it's like, we could stuff them together if that's not, but okay, I get it,
Yeah.
the end scale, okay.
Yeah, just to comment on that log of omega naught term.
Yes.
It turns out that that was two pi v times u naught to the power of m over two. And so when you multiply u naught over u naught and you have this f naught,
It's again,
if you had grouped beta fluctuation to include the log omega naught,
then that goes away.
and then basically everything cancels and you don't need that f naught and that constant that was troubling you.
Okay.
Basically everything cancels, everything works out.
So basically this F naught is minus log omega. It's kind of, is that,
Yeah, basically, yeah.
Okay.
Exactly. So in the top line, we use the time beta fluctuation.
that makes a lot of
If you
sense.
just if you group the log omega naught to that, then I'll concentrate.
Yeah, I knew that there was some utility to keeping omega naught around. I just couldn't remember exactly where it showed up. But yeah, no, that's perfect. Thank you. Yeah, and then, okay. And then like, if you didn't have that, then when you do this bit, like formally that constant would have a divergence in it, right? When you,
Yeah,
right, and so this corrects that. And so the only source of the divergence here is really from this term. Which we'll talk a little bit about. Let me see. So I can write out the whole free energy real quick. So the total free energy. Have beta F. Right, so there's a truly irrelevant constant that has like the Broglie wavelengths and stuff like that in it. Those we really don't care about because it is just some reference state. And then there's a term that's plus 1/2 rho naught squared u naught v. All right, so this density squared times u naught, that's like the mean field energy of the system, or the potential energy of the system. And there's plus v over 1 pi squared. There's the fluctuation term 0 to lambda c dk a squared log 1 plus u naught and rho naught dk. And I guess F0 also has the n log n over v term, the entropy of mixing term. Maybe let me just write that out. Since minus also n, but not v log rho naught. I think. Mentions that I don't like. There's a term similar to this that should be there. I forget exactly what it is, but it's. Anyway, that's the entropy of mixing ideal gas term. All right, but then once you have this Helmholtz free energy, like all the old equilibrium thermo rules apply, right? Like you can take d by d little n to get chemical potential. You can take d by minus d by dv to get pressure. You can look for inflection points in this thing to figure out when the thing will be thermodynamically stable or not. Like all that stuff comes into play here. All right. So that's the end of my written notes, and the other stuff that I was going to talk about was a little bit more about this cutoff that we had to introduce, and like what that actually is coming from in its origin. But I guess before I dive into that, let me ask, are there any questions about this stuff? All right, so this let's talk a little bit more about this lambda c. I'm going to bring up my notes just so I can make sure I don't miss any of the important points. All right, so this is kind of an artificial thing again that we introduced to sort of remove or at least control a UV divergence. And so in other words, what this means is that the interval does not converge as lambda c goes to infinity. Right, and if you think about the like discretization problem that we were talking about earlier, where we're taking our functions and discretizing them, what this lambda c represents, right? It's an upper limit on k. Remember, as you go to larger and larger k, that's shorter and shorter length scales, right? So that means that basically we're trying to resolve smaller and smaller length scales, but the problem is just not behaving for us, right? It's continuing to diverge. And so if you think about this in like the real space version of this, it would be like doing a, I don't know, a fluid dynamics simulation where you have, you're solving Navier-Stokes equations on a grid. You would expect that if you make the grid denser and denser and more resolved, things should converge to an equilibrium or steady state type of result. Like your answer should stop changing as you improve the resolution. And this is a symptom that will not happen for this theory as we have derived it. And that is actually a problem that you run into when you do beyond mean field simulations. And the origin of it actually comes from where we started with our interaction potential, right? So in this particular case, so the origin of this, and this is part of the stuff that where I was a little more involved in the conversations to figure this stuff out with Mike. But again, that same paper I think details this really nicely. But the origin of this UV divergence is in our use of the pair potential that was a constant times a delta function. So remember, this delta function is something that is infinitely narrow and infinitely peaked. Right? And so no finite amount of resolution is going to resolve something that's infinitely narrow. That's what this problem represents. And so it's really trying to resolve something that is just not resolvable. And that's sort of the, I guess, physical manifestation of this thing being a problem. And so there's a couple of ways that you can actually resolve this. And I guess, well, the first thing I'll say is that if you're only doing mean field calculations, this doesn't matter at all. It doesn't show up. Like you see that this interval only shows up in the fluctuation term. So for mean field calculations, it really doesn't matter. It only shows up when you care about fluctuations. And it also only shows up in some properties. It doesn't show up for everything. There are just some things that are UV divergent, and you have to be careful about it, some things that are not. But having this analytic expression to see where it comes from, I think is really, really nice. And then the way that you resolve it is to basically do something about this delta function. And again, that paper by Vallée, and then also one of my early papers after I started at Penn with Jason Kowski and Huquan Chao, we showed there's a couple of ways of actually resolving this that you can actually show are formally equivalent to each other. And so basically we have two places where there's delta functions that show up in our model. One is this pair potential, and the other is in the microscopic densities. Right, when we said that the sum of the discrete Gaussian beads are a sum of delta functions. If you make either one of those a Gaussian, or just smear them out over some finite range, it gets rid of this problem. Okay, and so let me see. I won't go through the equivalence. We're getting a bit long on time, but if we either let u of r go to become a normalized Gaussian, so 2 pi sigma squared over 3 times sigma squared. Right, so if we make this our parapotential. And repeat everything that we've done, right? So particle to field transformation, all that fun stuff. We're not gonna go through that details. But if you do this, or define the densities to be sum over I to sum over J, sum over S. This H of R being a unit Gaussian. We'll call it A squared. Again, these are just unit Gaussians, so that the integral of the density still gives you the same number. If you do either of these two things and trace that through all this particle to field stuff, it fixes it. And the way that this shows up, sorry, I'm trying to remember exactly the order that I went through this. Right, so this is either making the, you're either making the parapotential non-local by giving it a finite range, or the typical language that we use for this approach is the smearing the densities over a Gaussian. So the smeared density what you get is, so beta fluctuation comes d over 4 squared. It's almost identical. A squared log of plus v naught, rho naught, and gk. And the new thing that shows up in here is hk squared. HK is the Fourier transform of this Gaussian, so that's e to the minus k squared, a squared over 2. And so hk squared, the square of this function is just getting rid of the 2. So it's basically the same thing. It just decays a little bit more quickly. And the nice thing that happens is that what that means is that as you go to k equals infinity, right, as k gets bigger and bigger at this integral, this Gaussian term is going to kill off this term, right? Because this is going to decay really quickly. Then you'll have log of 1, and which is 0. So in other words, as k goes to infinity, this whole thing is going to go to 0. So then you can let that go for whatever arbitrary large length scale you want. And the kind of cool thing is that if you do the same thing with the non-local interactions, what you end up with is instead of hk squared, it's just uk. Yeah, it's the Fourier transform of the potential. And there are, well, Mike actually spent a lot of time playing with the 2 different implementations of this to figure out what works best when. I like the non-local densities better, but it's kind of irrelevant. You have a question, or was that?
No, I was just gonna say that's cool, that makes sense, because basically with the delta functions, you kind of have 2 infinities at the same time in some sense, and that's why you're going to the left, and so you have to truncate one of them basically, and it should.
Yeah, exactly. All right. Well, I think that's more than enough for today. So this is kind of one of the cleanest ways of analyzing systems where you want to incorporate fluctuations, which I haven't talked about when that's actually important. The obvious one is when you're critical points, right? That's sort of a well-known place where fluctuations become important. The other place where it becomes really important is for systems that have electrostatics and charges involved. So anytime you have charges, like, as I've said before, mean field solutions are just terrible. But again, you can incorporate fluctuations at this level and still at least get in a qualitatively right direction. Maybe not quantitatively, but a lot of the qualitative physics will be built in as a result of this. And because of Coulomb's law, it has that divergence at r equals 0. There is still a regularization problem, but if you smear the charges over a unit Gaussian, it fixes that as well. I think that's basically it for this part. And again, this is a good approach for dealing with macro phase separation. And what we'll deal with next time is micro phase separation, where you need to have like a, well, there it's convenient to have a structure factor to work with, see where that's going to diverge. So we have to go through the quote unquote other way of deriving a field theory, which is a little bit easier, and then getting the structure factor out of it. All right. Questions? Yeah, well,
Kind of, okay, so before you do like the fix.
Mhm.
Yeah. I'm curious, cause like, it's probably just in like the details, I can find this, but with like the UV divergence, like, is it like, an infinite sum kind of divergence, or is it like an oscillatory divergence, like as lambda c goes to infinity without fixing?
I think it's more like an infinite sum because you're like the argument of the integral, like if you just plot this function, like the thing just, I forget exactly what the behavior is. Does it level off to a constant? Do you remember, Josh? I forget if it levels off to a constant that just, so like as you keep integrating, it just goes to larger and larger.
Yeah, you just keep adding more.
I think that's right, because that's what the divide function is gonna go to 0, and you're basically summing up the log of. Anyways, maybe, I think it's a constant.
Yeah, I think it goes to a constant. Yeah, so it's not oscillating. It's not like trying to integrate a sine function. It is just like integrating something that just, it's like integrating y equals a constant, right? It just goes on forever. Yeah. All right, well, that's it for now. We will resume next week on either Tuesday or Thursday. I'm not sure which. I'll let y'all know. All right, well, have a good long weekend. Bye, Yuri.